Hey there, my name is Shane O'Leary, and today we're going to be doing what is called the fire balloon experiment. You're probably confused. What is going to happen in this experiment? Well, put simply, I'm going to be lighting these candles, putting this balloon over it, and seeing how long it takes them to burst due to the fire. So as I stated, going to be lighting up these balloons, and I want you to make 4 predictions. Which balloon will last the longest? We have the balloon full of air, the balloon full of 25 milliliters, the balloon full of 50 milliliters of water, and additionally, there's a balloon which I haven't filled yet, which I will fill with 25 milliliters of cold water. And I haven't filled it yet because I want the water to stay cold. So I want you to predict why you think, which one do you think will pop last? And thank you. The experiment will begin soon. Alright, so it's now time to begin the experiment. I'm going to start off with the balloon filled with air, followed by the balloon filled with 25 milliliters, then 50, then the one full of 25 milliliters of cold water. So with that, let's begin. 3, 2, 1, go. Alright, so now doing the 25 milliliters of water. Alright, third experiment, third video. Let's do this. As you know, this balloon is filled with 50 milliliters of water. Got our candle, got our lighter, but first I'd like to talk about the fascinating specimen which was recorded last video with the 25 milliliters of water. In that video, the balloon did not pop, but instead sprung 3 holes in which all the water leaked out. And then the balloon proceeded to, so all the water and air leaked out of the balloon, then it proceeded to melt. And since I don't want melted rubber all over this fine stovetop, the video concluded. So we'll get to that more in the explanation section, but now, let's begin. Go. The candle went out. So like the balloon popped because I hit it with this lighter, but still, like that lasted. Didn't record it because once again, I didn't even mean for this to happen. So this final one, this is the cold water one. It's a balloon. It's filled with cold water, 25 milliliters of cold water. So yeah. Hey there! I'd like to congratulate you for reaching the end of the video. This is the explanation portion of the video. And let's not drag this on for too long. So let's begin. So first off, water is a polar molecule which is held together by hydrogen bonds. That does not play too much of a part into this video, but I felt like I should mention it. Really the only thing that plays a part into it from that
is hydrogen bonds. When they heat up, they start to break apart a little, which spreads the atoms so they can transfer the energy throughout the balloon. With that, let's begin. So first off, we got the balloon with air. And before we get into that, there's a couple things we should go over. First off is the term specific heat capacity. Now, what specific heat capacity is basically how much energy it takes to heat up an object, specifically 1 kilogram of material by 1 degree Celsius. That's not important. How much energy it takes to heat up an item. Now, the specific heat capacity of water is 1400 joules per kilogram degree Celsius. And of rubber, which is what the balloon is composed of, it is 1600 joules per kilogram Celsius. Now, this is important because when we heat the balloon with just air in it, there's like no water barrier. So it's going directly to the balloon. Scooby-Doo, 4 TV episodes, Monster Tales, from the What's New Scooby-Doo series, as well as Scooby-Doo and the Goblin King. Now, this one's pretty good, but this one is not a favorite of mine, but it's still here, so let's do it. So this here will be our fire, and it is heating our rubber balloon right here. Transferring thermal energy into it is starting to heat up. Like I said, the specific heat capacity is only 1600 joules per kilogram degree Celsius, and the melting point is 120 degrees Celsius. Now, fire produces a lot of energy, so it's producing enough energy pretty soon, produces enough energy to pass the specific heat capacity. The temperature in the balloon starts rising. Eventually, all the atoms inside, transferring thermal energy to each other, eventually hits the melting point. The rubber melts, it gets a hole, all the air comes out, it pops, and that's about it. Next up, go in our balloon with 25 milliliters of water in it. This is our fire, but this time, as stated, water's in the balloon, and it's acting as a natural barrier, absorbing all the thermal energy, then transferring it through the balloon. So the thermal energy comes up from the candle, goes into the water, which then gives it to the balloon, and its specific heat capacity is 4200 joules per kilogram degree Celsius. So almost around 3 to 4 times, or 2 to 4 times, the amount of the rubber specific heat capacity. So let's get into it. Fire, this quality DVD right here, is heating our balloon. It's going into the water. The water, it takes a little longer to heat up, and the water is taking longer to heat up. And by the way, I should probably mention this, that the boiling point of water is 100 degrees Celsius. So it's a little bit lower, so it's, that's about it. It's a little bit lower boiling point, so if the water boils, obviously the balloon is gonna pop. But that is countered out by the fact that it's gonna take longer to heat up the water because it has a higher specific heat capacity. And because it's going to take longer to heat up the water, it's going to take longer to heat up the balloon, because the water can't give more thermal energy to the balloon than it takes to pop. So thermal energy goes in here, takes a little bit longer to pop because water has a higher specific heat capacity, takes longer, moves through, can't give more to this than it already has, so it takes longer to pop. This one, the 50 milliliter one, I think I already explained this. I'm gonna go with what was supposed to happen in the 50 milliliter one, and why it should take longer is what I will be explaining, rather than the unaccounted variables, which I did not account for, making them unaccounted. 50 milliliters. Why, in theory, should it take longer to pop, and in most experiments does take longer to pop, if you are not a fool who doesn't take in all variables. Alright, so once again, got our fire, because it slaps, bangs, great fill. Got our balloon filled with 50 milliliters of water. It's cold, wet, no one likes it. No one even wants to be near it. It's heating up, water's going in. Fire's going into the water. Water's giving that thermal energy to the balloon. But there's more water this time, which is where our good friend, the orange, comes in. Perfect orange right here, great. It's in fine condition. And this is gonna be our little analogy metaphor thing. So, this is why more water takes longer to heat up and therefore takes longer to pop. So let's say I'm peeling an orange. I don't know how to peel an orange, but let's hope you do. So let's theoretically say that I did peel this orange by some miraculous means. I use a little bit of energy, let's say. I use my energy, peel it right open, it's fine. That's a delicious orange right there, very juicy. So I use my energy, peel it open, but let's say this orange is 50 million feet high, very tall, very big, very circular, very orange. If I use that same amount of energy, which I used to peel this orange, to try and peel that orange, it's gonna take a lot longer. There's a lot more to peel. I just rip this open, nice and easy. Orange is big, doesn't work that way. It's just, you can't do it. Now, why does that happen? Well, we got this formula right here. Q equals mc squared T. Now, what does that mean? Well, Q is energy, M is mass, C is specific heat capacity, and square T is change in temperature. Now, volume in water is equal to mass, which means if we increase the volume, because of our rules of how equations work, it is going to also increase the Q, because if you increase one part of the equation, like 5 plus 7, increase it to 8 plus 7, it's going to go up, the final product. So that Q, that energy, it's going to go up. So you increase the mass, that's going to increase the energy needed to move the thing, and vice versa. And that's how it works. You increase one part, you increase the other, and energy is equal to time. So it's going to take all around more time. Heat, water, heating, there's more water. Because of that, more volume, more mass, more energy, more time. Taking more time, a lot more atoms to transfer thermal energy to, a lot more hydrogen bonds to get messed up a little as they transfer that thermal energy. But the point is, they're cool. They transfer that thermal energy, it just takes a little bit more time. Takes a little bit more time to boil, takes a little bit more time for the energy to go into the balloon, that means. Takes a little bit more time for the balloon to pop. It pops, and that's what happens. Now, cold water. Got Shrek 1 here, and Shrek 2. So this, Shrek 2, because it's better, is our fire, and Shrek 2 is our cold water. But even though it's cold water, it still slaps. Heating up the water in the balloon. The water in the balloon is a lot colder. And because it's a lot colder, I'm sure this is all basic, cold water takes longer to heat up because it's colder. Now, if I had a balloon that was 0 degrees and I wanted to bring it to 50 degrees, let's say that takes 5 minutes. But if the balloon is if the water's now negative 50 degrees and I want to bring it to 50 degrees because it needs to increase by more degrees, that's going to take more time. And that's the science behind it. This heats it about the same. It has the same specific heat capacity as the 25 milliliter one, because it was full of 25 milliliters of water. But since it's so infinitely colder, it's gonna just take more time because we're trying to raise it by more degrees, which means it's gonna take even more time for it to transfer that energy right into our good friend, the balloon. So that happens, it heats it, takes a lot more time because it's a lot colder, transfers that energy. The balloon eventually hits boiling / melting point, it pops open, gets cold water everywhere, and then I'm covered in boiling water.